Uh, Good afternoon. It's a pleasure to be here, and I'm very grateful to the organizers for inviting me here and for organizing this great program. It's a pity that I will have to leave tomorrow. I will come for 1 week. I'm teaching back at home. So this talk is about. Whoops! Just a moment. I need to learn quickly how to do it. Yes, this talk is about fluctuations of current, large fluctuations of current mostly, in some non-stationary settings with very simple diffusive lattice gases. And my collaborators are Pavel Susorov from the Institute of Applied Mathematics in Moscow and Arkady Vilenkin from my home university. Okay. I'll start with briefly reminding you about diffusive lattice gases, and then I'll briefly introduce the macroscopic fluctuation theory developed by the Italian group of Professor Iono Lasinio and collaborators. And then I'll define the problem that I'm using here in this talk as an example of the power and insight that you can get from the macroscopic fluctuation theory, statistics of current on an infinite, passing through a point on an infinite line. And then after formulating the problem, I'll show you two different perturbative approaches that can be used to extract analytical results. One of them actually probe typical fluctuations, small fluctuations, relatively small fluctuations, and the other approach probes very large fluctuations, essentially the distribution tails. And while doing it, as I will try to convince you, it turns out that similarly looking simple lattice gases actually can be divided into two universality classes, which we call elliptic class and hyperbolic class. So, and we can, use this slang as call them elliptic gases and hyperbolic gases. And then I'll show you some specific results for the SEP, simple symmetric exclusion process, and for the KMP model, Kipnis-Marchoro-Prisuti model, that turn out to be the simplest representatives of each of the two classes. And then I'll summarize. Okay, a brief reminder about diffusive lattice gases. It's lattice gases that are symmetric in their dynamics, so there is no bias, and there is just motion from a side to a side. So the simplest of them is really random walkers, independent random walkers, where each particle can hop either to the next side on the left or next side on the right, and it doesn't matter whether the site is occupied or not. This is random walkers. Zero range process is a generalization of the random walkers in the sense that the rate of hopping to the left or to the right only depends on the number of particles in the departure side, and zero range process also doesn't care whether the site is occupied or not. And there's a family of exclusion processes, and them that the simplest is the simple symmetric exclusion process, which is governed by the same dynamic, microscopic dynamics as the random walkers, except that a move, for example, this particle, if it sort of decided, or actually we decided by playing the roulette, moving to the right, the move is disallowed because this site is occupied. So this is the only change, and of course this modification is quite dramatic. Now there are also models of the type of KMP, Kipnis, Marchoro, and Prisuti. This model, there are no particles there. There is a lattice, and each side of the lattice includes, let's say, an agent. There is an agent on each side of the lattice, and these agents have some energy, and this energy is not an integer number, it's just a real positive number. And the dynamics, it looks like this. You take two neighbors, they put the energies together, and then they again redistribute the energies among themselves according to the uniform distribution. Okay? So this is the rule of the game, microscopic rule of the game for the KMP model. So these are three, or actually four examples. There are many, many more. So there is essentially a huge family of microscopic processes that can be cast into this diffusive lattice gases paradigm. And what I'll be interested in, actually, what I'll show you now, the equation that I'll show now will be a starting point for me. So the starting point is not the microscopic description, but actually some already large-scale description, what we call here fluctuating hydrodynamics. At the level of fluctuating hydrodynamics, when I already am interested in long times and compared to the hopping time, for example, or energy exchange time, and large scales compared to the lattice side. These scales, this family of lattice gases is described by this Langevin type stochastic partial differential equation, where the deterministic part is just simple diffusion, simple or a little bit less simple because the diffusivity can depend on the density itself. So it's a nonlinear diffusion equation. And there is also the noisy term, of course, the number of particles, all the total energy is conserved. So this noise is under the divergence. And this is the Gaussian noise, delta correlated both in X and in T. And it is so because we are interested in long times and large scales, and viewed from these long times and large scales, the correlation time, which is of the order of the hopping time, and the correlation length, which is of the order of the lattice constant, already can be sent to zero. And you can read about the theory of how to get these equations and their properties in the book of Herbert. It's already a classic book written 24 years ago. So what is important for us here is that at the level of macroscopic description, all this family of diffusive lattice gases are completely characterized by two functions: the diffusivity as a function of rho, and the mobility sigma of rho, which determines the fluctuations. Okay, so for the completeness, there is a relation between d sigma and the free energy density of the system. So the second derivative of the free energy density is just 2d over rho. This is an analog of Einstein-Kubo relation. And so we need two functions for each gas, and then we can calculate the third one. So that's it. So for the simple examples of the diffusive lattice gases that I showed, three of them, the random walkers, the SEP, and the KMP, have a constant diffusivity that can be rescaled to be 1. And for the zero range process, the diffusivity is the derivative of the departure rate with respect to the number of particles. And of course, this has any meaning only if this quantity is positive. Otherwise, hydrodynamics just doesn't work for the zero range process. There is condensation and things like that. But at the level of fluctuations, all these models are already different. As you see in the random walker, sigma is just proportional to the density. For the SEP, it's 2R, 2 density times 1 minus density. And for KMP, it's 4 density squared. And as you will see in the following, this difference is crucial, or can be crucial. Okay? So the macroscopic fluctuation theory, I feel humbled and privileged, to tell you about it in the presence of Gianni Lasinio. This series of works that started around 2001, about 15 years ago, and culminated in the last year's review of modern physics that they wrote, Pertini, De Soli, Gabriele, Lasinio, and Landim. They developed essentially an extension of the Freidlin-Wenzel weak noise theory, originally developed in the context of zero dimensions for the Fokker-Planck, Langevin and Fokker-Planck. They extended it to fields specifically coming from the lattice gases theory. It can be also viewed as a WKB theory, an analog of WKB theory, but a dissipative WKB theory, which as a small parameter uses 1 over the typical number of particles or lattice sites involved in the dynamics. Okay, so let us continue. Well, technically, it can be derived, the equations of macroscopic fluctuation theories can be derived, actually they can be derived in several ways. They can be derived directly from microscopics, but historically they were derived starting from the fluctuating hydrodynamics and essentially exponentiating the action of the Gaussian, white Gaussian noise. And in the leading order, what they did in a more physical language is equivalent to a saddle point expansion of the path integral, and this was explicitly done a few years ago by this group. And when you do the saddle point, you naturally arrive to the problem of minimization, minimizing a functional. And at this stage, you already identify some classical mechanics, some classical field theory, which is mechanics in its nature. So then, when you recognize it as mechanics, you can work alternatively in Hamilton-Jacobi representation. This is mostly what Gianni and his collaborator did in many of his papers and most of his papers. You can use the Lagrangian picture. Okay, you can use Hamiltonian picture, which sort of I like more, and we've been using it mostly. So at this level, if you work in Hamiltonian language, the saddle point equations, just look at Hamilton's equations. Q is the density, and P is the conjugate momentum or momentum density that sort of you acquire by doing by going from the noisy problem to essentially the deterministic problem coming from the saddle point approximation. And we use just Q and P for the density and the momentum field just to stress its Hamiltonian properties and its relations to classical mechanics. So these are the equations. You see these functions, d of Q and sigma of Q enter these equations. And these equations I did Hamiltonian. You can identify Hamiltonian, and H is the Hamiltonian density, which has this sort of part describing the deterministic terms and this part describing the fluctuating terms. So let's see the main properties just briefly. So these are the equations. Please.
Momentum have physical interpretation?
Oh, it's a very good question. Yes, it does have a physical interpretation. It describes, intuitively speaking, P describes the magnitude of fluctuations. So you will see it immediately. It's because, well, first of all, let me continue, and I'll touch this question in a minute. These equations in themselves, I mean, they're not very informative because these are two coupled nonlinear PDEs, and they have huge amount of solutions. And of course, the problem becomes meaningful once you supply boundary conditions in X and T, and these are problem dependent, and these are actually come out when you really minimize what you need to minimize starting from the beginning and treating, the boundary terms, after integrations by parts. And then you acquire the boundary conditions. Some of the boundary conditions are obvious, some of them are not, but these are problem dependent. Now, what is important is the moment that you put P equals 0, Henk, I'm trying to answer your question, you see that the second equation becomes an identity. Well, the first equation degenerates into the deterministic motion. This is the deterministic manifold. This is an invariant manifold of this little world, which describes the downhill trajectories. So if you condition your problem on reaching some, an unusual state, you want to study some large deviation, then you need an activation trajectory. So you need the fluctuations to work. You need P not to be equal to 0. So you already see from here that the larger P is, in some sense, the stronger fluctuations are. But in many specific settings, we can give a bit more specific and a concrete meaning to P. But speaking in general terms, this is what I can say. So P describes a sort of the magnitude of fluctuations. Now, once you solve these equations with the boundary conditions that are problem dependent, then you can go back and evaluate the action, which is just the mechanical action. But for this lattice gas, you get this formula. So when Q and P as a function of space and time are known, you can compute this thing. And then you know up to a pre-exponent that you don't care in this leading order of the WKB-like theory, you evaluate the probability of a certain large deviation in question. So this what is correct if the initial condition is deterministic. If the initial condition is random and you want to average also over the initial conditions, then you actually don't know what the optimal initial condition will be that contributes the most to the probability or makes the action minimum. So you need to include here the Boltzmann-Gibbs free energy cost of creating the optimal initial condition. And it's needless to say that having solved this problem, you actually find the optimal path that the system, optimal history of this system, density history of the system towards reaching a given large deviation at a given time. So it gives you a lot of additional information, physical information and intuition on top of evaluating the probability of this event. And this, I think, is the most important single advantage of the macroscopic fluctuation theory compared to direct methods where you evaluate the probability. Okay, the MFT emerged in the context of a non-equilibrium steady state of diffusive lattice gases, where usually you prescribe you put two reservoirs at different temperature or different densities. The system has size L, and then the expected density profile solves the steady state mean field equation with these boundary conditions. But you're interested in the fluctuations of the density profile, and this probability of this fluctuation has this form of an exponential with a large deviation function, which naturally is rescaled with the size of the system. The size of the system enters here and here. And if you want to find the probability that the density profile is very unusual, very different from a profile coming from this equation, from the deterministic profile coming from this equation, you essentially need to find an optimal path of the system starting from time equals minus infinity and reaching the prescribed density profile, and then you can find this large deviation functional just by computing the action that I showed you. And the other typical problem that the MFT emerged in the context of is the same setting, but you're interested in the average current, in the current through the system and how it depends on the rho minus, rho plus, and system size. Again, the average current is just a function of rho minus and rho plus. For example, for independent random walkers, for the SEP and for the KMP, it would be just a difference rho plus minus rho minus divided by L. In other models where the diffusivity is nonlinear, it will be a more complicated function, but it will scale with L. But the true current through the system fluctuates, and you want to know the probability of these fluctuations. And again, there is a natural scaling with the size of the system. There is the system size here and system size here in this definition of the current. And you need to find the large deviation function and the optimal path that corresponds, or rather optimal profile. And here is already the question, is this optimal profile stationary for all J? Or maybe there are some motions that at large currents. It turns out that this problem is not yet proven it's not yet solved for a general lattice gas. The simplest case is just a stationary density profile, an unusual profile which contributes most to an unusual current that you condition on. But it turns out that it's still unknown whether for any model and for any current that you condition on, the optimal profile is stationary. I thought that it was solved long ago. It turns out that it is not. Okay, so these stationary problems, non-equilibrium steady states of lattice gases have provided a tremendous, dramatic improvement in our understanding of non-equilibrium systems. I'll only mention long-range correlations. The fact that the uphill trajectory, in the language of MFT, is very different from time reverse downhill trajectory, and also dynamical phase transitions, non-smooth parameter dependence of the large deviation functions of functional. But actually there are many other problems and many other settings where the macroscopic fluctuation theory or its extensions can be used. So today I'll be talking only about one of them, but there are many others where this theory can be put into good use. And I'll be talking about fluctuations of mass or energy transfer through a point on an infinite line. So we have an infinite line. We start with some profile of the density or temperature, for example, a step light profile. And I'll be talking only about the deterministic profile in this talk, although there is a sort of parallel problem where the initial profile is random. And of course, that story is a bit different. So this problem was formulated by Bernard Derrida and Antoine Gershenfeld, who was at the time his PhD student. And then several papers continued studying this problem. So you start from this density profile, for example, and you want to know how much material or energy, if this is energy, have passed through the point x equals 0 by time t. Okay? So in the deterministic limit, when you completely ignore fluctuations, you know that this profile will just evolve in a diffusive fashion. If it is just, SEP or random walk or KMP, it will be a simple error function solution. So you can compute at any time t how much material have passed from left to right. But of course, in the microscopic system, this quantity will fluctuate, and you want to know the probability distribution of this fluctuation. So essentially, you condition your problem on these integrals. So you subtract the initial density, which is actually rho plus here, from the density that you will observe at time t equal capital T. You integrate it, and this is the current that has passed. Okay? And so now there is no analog of capital L. The system is infinite, but very naturally, at least at the physical level, one quickly realizes that what plays the role of the system length is just the square root of t, or its analog for more complicated diffusion problem. It's just the typical diffusive scale. So you expect that not only the deterministic result, but also the statistics, the probability distribution will show self-similarity, which shows scaling with this square root of t. Here I put it for the simple models when the diffusivity is constant. When the diffusivity is not, well, actually it's square root of t for every model. Sorry, I take it back. It's a very specific initial condition. Yes. So, and this is what Derrida and Gershenfeld realized. And this is what the problem that they formulated. So the objective here, oh my God, sorry. The objective here is to evaluate the large deviation function, or in the language of the macroscopic fluctuation theory, is just the mechanical action, which would depend on the rescaled current and on the densities rho minus, rho plus. There are no other parameters in the system at the level of the macroscopic description. Actually, even if rho minus is equal to rho plus, so it's a flat initial profile, the problem is still highly non-trivial because it's a deterministic profile and you condition on something happening at a finite time. Okay? So even this problem is non-trivial. It is simpler technically, but it's not. Now, an interesting question is what is the optimal history of the system conditioned on this J? And this is not an additional question. As always in the MFT, you first answer this question and only then you are able to evaluate the action, the mechanical action on the trajectory, the mechanical trajectory that you have found. Okay, so Derrida and Gershenfeld actually derived the full MFT formulation of this problem. So the equations that come out, it's just one-dimensional version of the equations that I showed you 5 minutes ago. The initial condition is very simple. It's deterministic step-like initial condition, so we don't have any problem with that. But the other, well, of course, there are also simple conditions that Q at minus infinity is just rho minus, Q at plus infinity is rho plus, and the momentum at plus minus infinity must be 0, otherwise the action will be infinite and the probability will be 0. But this boundary condition is non-trivial. Actually, you need to do the minimization when you impose an integral constraint. So these difference of the density at time t and density at time 0 must be equal to a certain number. This obviously calls for a Lagrange multiplier because you need to add lambda times this integral to your action that you minimize. And when you walk through the derivation, you see that this gives you a boundary conditions at t equal t capital T. The momentum density as a function of x at t equal capital T must be proportional to the Heaviside, to the step function at x. And lambda is this Lagrange multiplier that is unknown beforehand, but then it is ultimately fixed by the demand that the current that you have passed is exactly equal to J. Okay, so this is sort of a well-defined problem. But unfortunately, well, it's hard. I mean, it's two coupled PDEs. There is no hope at all that there is a simple, steady state solution or something that will, like this, that will do the trick for you. So you really need to solve it. So as a result, what Derrida and Gershenfeld only did in their paper in 2009, in the context of the deterministic initial condition, I emphasize, is just solve it for the random walkers. For the random walkers, this problem is just solvable analytically, completely and exactly, because once you do the Hopf-Kohl transformation, your equations become first decoupled, this for Q and P, and both of them are just diffusion equations. One of them is the diffusion, and the other is the anti-diffusion. That's it. So you solve the anti-diffusion equation with the initial condition for P backward, then you plug it into the equation for Q, propagate it to the positive times, and you compute everything. This is a very nice exercise, but it has nothing to do with interacting particles. So what can we do in other cases? In this problem and in many other problems that can be dealt with in the language of MFT. First, there is a very good numerical algorithm which is especially was developed to deal with this mixed type of boundary conditions where you prescribe the density at t equals 0 and the momentum at t equal t capital. And there is a class of problem with this type of boundary conditions. And this algorithm was developed 14 years ago by Chernych and Stepanov in the context of a completely different problem. They were interested in the turbulence coming from the Burger's equation. Burger's equation pumped by noise. And an analog of MFT, which existed from the mid-90s in the context of the Burger lens, Burger turbulence, just dealt with the coupled equations for Hamilton equations of a similar structure. Also, in that case, they are not really local. So one of them is the equation for the momentum is non-local. But this is the iteration algorithm that they suggested, just propagating the equation for Q in our language forward and equation for P backward, and the algorithm converges very, very quickly, at least for the models that we worked with. But I'm not going to talk today about the numerics. Today I'll be talking about two perturbative approaches based on the addition on the existence of additional small parameters. Well, one small parameters we have already used is the typically the noise is weak. The typical noise is weak. This is what brings us from the Langevin equation to the macroscopic fluctuation theory in the first place, okay? So this one is already used. The question, are there any additional small parameters in the problem that can be used, to develop a perturbation theory? And there are two natural cases, not only in this problem, but actually in some other problems as well. It's first, if you are interested in more or less typical fluctuations, not so far from the peak that is predicted by the deterministic theory, you can use the fact that actually J minus J, average J, so the current minus the typical current, or for a flat initial condition, just J is in some sense small. So you're probing the region of the Gaussian distribution and maybe several additional cumulants. In this case, you can easily figure out that you are talking about a small lambda. So the lambda, the Lagrange multiplier, plays the role of the small parameter of the theory. This is quite natural because the moment you put lambda equals 0, it means the momentum is equal to 0 At the end, it will be 0 all the time, and you're back to the deterministic manifold. You land on the deterministic manifold. So exploiting, perturbation theory with respect to lambda order by order will give you the opportunity to go farther and farther from the peak, from the Gaussian distribution. And the other approach is quite different. You just assume that the current is, large in a crazy manner. It's huge. In this case, the intuitive thing to try is to think, okay, if we condition on a huge current, then probably the diffusion terms in the MFT equations are very small compared to the terms that come from the fluctuations. So maybe you can exploit this as a zero-order perturbation theory. So let's see how it works. So small j, small lambda expansion works very nicely, and it's quite a universal theory. It can be used and has been already used in a couple of other systems. You just develop perturbation expansion for the density, where this is the expected, the solution of the deterministic diffusion equation. And then you just put here lambda q1, lambda squared q2, and so on. And the p starts from lambda. So there is no zero-order term, and the zero order is just 0. Okay, so it turns out that the simplest case, the case can be really worked out in detail, is the family of lattice gases where the diffusivity is constant, while sigma can be arbitrary. In this case, we have a very nice and simple unperturbed solution. In the first order, we get equations like this. This one is just a linear anti-diffusion equation. It decouples from this one. You solve it with this boundary condition at time t equal to capital T. Then you have the solution as a pump, as a drive in the equation for Q1. You solve it in a standard manner. And in the first order, you already get the variance of the distribution for all lattice gases with a constant diffusivity coefficient. So it shows the expected scaling with time. And this is a sort of a closed form relation. You just plug your sigma, your mobility coefficient as a function of the density. You compute this double integral, and you get this variance for all lattice gases. If you continue to higher orders, you will get higher cumulants. The second order will give you the third cumulant, and so on. Okay, so you can, if you're not lazy, you can, compute quite a number of cumulants in such a way. Let's go to the more interesting case of very large lambda. What if we really implement this naive approach and just drop the diffusion terms in the MFT equations? What you get immediately, you get a tremendous reduction of the order of the problem. There are two diffusion terms here in the equation for Q and the equation for P. I drop them. Here, by the way, it's V of x and t. It's just the gradient of P. It's more convenient to differentiate the second equation. Now we have two conservation laws, which have the character of Euler hydrodynamics. Okay, so it's a hydrodynamic terms. You have some boundary condition for V. It's just the derivative of the step function. Now it's a delta function. And people, like about 100 years ago, probably was Riemann, I'm not sure, developed a nice trick, which is by now completely forgotten, how to solve exactly many of the problems like these of ideal hydrodynamics. It's called the Hydrograph transformation. The Hydrograph transformation actually does a very strange, very crazy trick. Instead of working with Q and V as a function of x and t, we go to t and x as a function of q and v. We completely sort of reversed the order of things. And it turns out, just after standard algebra, that these two equations can be brought into a single linear second order PDE for t as a function of q and v, or for x as a function of q and v, doesn't matter. So this is the second order linear PDE. I'm emphasizing linear. These two equations are nonlinear, but they only have first derivatives with respect to t and x. And it turns out that it is sufficient to get, in a general case, to get a linear equation. And now, of course, as any linear second order PDE, you can classify this equation into three classes. Okay, and in this case, everything depends only on the second derivative of sigma with respect to the density. So when this guy is positive, it's a hyperbolic class, like the wave equation in physics. If it is negative, it's an elliptic class. It's like Laplace equation. And in a very special case, actually, of random walkers, when this derivative becomes 0, so there is only 1 second derivative with respect to v, this is a parabolic class, like the heat equation in physics. So now you see that there are 3 different cases. And by the way, SEP is always elliptic, because for the SEP, this sigma prime prime is equal to -4, while the KMP is always hyperbolic, because this second derivative is equal to +4. Oh, well, let me talk about it a bit later. Now I'm just talking about the properties of the equation itself. And of course, the boundary conditions are essential to make the problem unique and so on. But even before that, we know that for the elliptic class, the only way, in the elliptic class, it's very natural to satisfy these boundary conditions. V, one of the 2 hydrodynamic fields, at t equals capital T, must be a delta function. And it makes sense, because if you're talking about the elliptic hydrodynamics, which is hydrodynamics, ideal hydrodynamics, would say with negative pressure, or with pressure that goes down as the density goes up, instead of acoustic waves, you have instability. So, and moreover, for the elliptic problem, you develop a finite time singularity. So it's very natural for the elliptic problem to develop a desired type of singularity at a desired time. While in a more familiar hyperbolic class, okay, where you have just waves propagating to the left and to the right, more or less, in the language of linear theory, it is impossible to develop a singularity. If there is a delta singularity at time t equal t, it must have been present all the time. And hydrodynamics, standard Taylor hydrodynamics doesn't know very well how to deal with delta functions. It knows very well how to deal with jumps, with shocks. This is a very natural type of singularities in Euler hydrodynamics, but not delta functions. And to deal with delta functions, you need really to go back to take into account the diffusion, to see how the diffusion regularizes these singularities, and then to continue and maybe use time scale separation and length scale separation. Okay, so these are 2 different strategies. For the elliptic gases, like the SEP, you indeed can drop in the leading order. You indeed can drop the diffusion term and solve the inviscid Hydrograph equation. This was our strategy a couple of years ago. For the hyperbolic cases, the situation is more complicated. You need to take diffusion into account, and you can use the inviscid equation in the outer region and regularize singularities, which will not be deltas, that will be sharp pulses, to get explicit solution for these pulses, to match them, and to compute what is needed to compute. And this is what we also did a couple of years ago for the KMP. Okay, now very briefly the results. Again, for the example of the SEP. For the SEP, very large currents, this is the Hydrograph equation after you use the sigma of Q of the SEP. And as you see, this Hydrograph equation is separable. So you just can, it's a linear equation, it's separable. So you can solve it just by separation of variables. But it turns out that there is an additional trick. And if you introduce an additional variable, a fictitious variable, you can transform this huge and not nicely looking equation and just into a Laplace equation in a 3D geometry. And the flat initial condition, it turns out, I'm talking about the initial conditions now, defines a Dirichlet problem in a cone geometry. So this cone actually comes, the angle of this cone actually comes from the initial density. For example, for the initial density of the half filling, this cone just becomes a disk and the problem becomes quite simple. But now you need to solve the Laplace equation with the boundary condition at infinity and with the boundary condition of this cone and the regular solution everywhere. And this is quite a mess. I mean, we worked for 2 years to get this solution, and you get solution in a complete way. This is how it looks like when we are going back from the Hydrograph plane to the physical plane. So this is how you transfer a huge amount of current in the SEP through this point 0. So in the beginning, you have a flat density. Then you develop, this hole. And this hole just increases with time. And you pass more and more current in the form of a densely packed cluster. And at time t equal capital T, all of this material in this hydrodynamic theory is just transferred into this material. And we have an explicit solution for all this stuff. And when you compute the large deviation function, you have this scaling, which actually was predicted by Derrida and Gershenfeld. And as we showed, the result is universal for the whole elliptic class, but only for the elliptic class and not for the other class. And this large deviation function, or rather the coefficient dependence of the density, is quite fun. It has a corner singularity at the half density. Okay, I'm finishing. I have 20 seconds left. It's a pity. Now, when we go to the KMP model, we need to regularize these badly behaving hydrodynamics by going back to the diffusion. But for the KMP, it turns out not to be so difficult because the KMP model just admits exact soliton-like solution. It's just, coupled pulses of Q and V propagating with a constant speed. And these guys serve as building blocks of the theory in this case, because what we need to, this is a sketch, what we need to do actually, we form these two solitons, or the solution forms this soliton at some distance from 0, and then they propagate, they adiabatically change. This Q pulse collects most of the available energy, but not all of it. There is some tail that we can compute, and it brings it exactly at the needed moment to x equals 0. The moment it crosses this, it did the job. And the large deviation function is very different now. Instead of being super Gaussian, as in the previous case, now it's sub-Gaussian, and it has this funny analytic structure at large densities. And now there are some other non-stationary settings that I don't have time to talk to. There is a whole list of other people working on, because these are other people, I will just flash the names. There is a very nice paper on the statistics of the position of a tagged particle in a single file diffusion. Krapivsky, Malik, and Sadhu, and the melting of an Ising quadrant at 0 temperature. This problem can be mapped to the SEP. It's very similar, but the same 3 authors developed it a year ago. So my summary. So the bad news is the complete statistics of fluctuations of integrated current is still unknown in the problem of Derrida and Gershenfeld, except for the random walkers. Macroscopic fluctuation theory yields the variance in the most simple way under these limitations. And it also yields far tails of the distributions for the SEP and KMP models, which exemplify the elliptic and hyperbolic universality classes. And well, these perturbative approaches, as I said, are also useful for other problems that MFT can deal with. And well, this is the take-home message. Each new solved example improves our understanding of large deviations and develops intuition without which it's very hard to work. And thank you very much for your time.